of light, number 35. So, how did that happen? What was the magic behind it? So, broken glass goes in, and then it restores itself.
Since the dawn of time, people have looked to the sky and seen omens and miracles in the extraordinary lights and colors. Rainbows were seen as bridges to the world of the gods, sun halos as the headgear of angels, and mirages as glimmering cities in the distance. But with our modern scientific understanding, can they all be explained through known principles? As light passes through the Earth's atmosphere, it is affected by changes in temperatures, as well as particles in the air. Contrary to our common understanding, sunlight does not always travel in straight lines. It bends, bounces, and refracts, creating a host of dramatic atmospheric optical effects. Everything our eye perceives is in one way or another a trick of the light. For example, if the sun gives off white light, why is the sky blue? Look to the sky and seen omens and miracles in the extraordinary lights and colors.
Why is the sky blue? We'll get back to that discussion one more time.
Rainbows were seen as bridges to the world of the gods.
Notice that you got red on top.
Sun halos as the head.
Why is this red on top when it comes to
headgear of angels?
Violet is going to be at the bottom.
And mirages as glimmering cities in the distance. But with our modern scientific understanding, can they all be explained through known principles? It bends. Everything.
And mirages. Speaking of the rainbows, once again, the red is going to be on top, the blue, the violet is going to be at the bottom. So the question is why? White light breaking into its color components, we call that dispersion. What's causing dispersion? On top of that, the reason why red is on top and the blue is going to be at the bottom is something that we discussed before, and we will get to discuss it again. This time we will discuss it a little bit more mathematically. So these are military airplanes. How do they evade radar? How do they become radar invisible? So this stick immersed into water is going to look bent. So the question is why? Obviously, this is something that we discussed before. It's called refraction. And we're going to take a look at it one more time. This time we will end up expressing the ideas much more mathematically. Diamonds sparkle. The question is why? So the same questions, except the discussion is going to be a little bit more mathematical. All right, so we're dealing with optics. Optics is the visible portion of the electromagnetic wave spectrum. So that's what we're going to be focusing on. And one of the things that we need to focus on is the wavelength. We'll do a comparison between red and violet. And these numbers are going to be expressed in terms of 10 to the minus 7 meters. So let's just focus on red. Red is going to have a wavelength, which is roughly about 8. The violet is going to be roughly about 5. So red is going to have a wavelength, which is going to be larger than violet. All right, so speaking of light, from the modern perspective, the light is being generated by electrons undergoing quantum jumps inside atoms. So the electrons jumping around inside atoms will just glow, which means that they will emit light.
An oscillating electric charge creates waves.
This becomes the classical version of it. Oscillating electric charge, in this case, it is the electron inside.
Propagate along the lines of
the oscillations or the accelerations of these charges is what generates the electromagnetic
force
waves.
at the speed of light. These ripples are transverse waves in the electric field, propagating in wave fronts that become flatter and flatter farther from the source, coming more and more to resemble the plane parallel wave fronts that are called plane waves. As the wave fronts pass through each point in space, the electric field vector oscillates up and down, marking the passage of peaks and valleys of the propagating wave. Thus, an oscillating electric charge is indeed the source of outward spreading ripples in the electromagnetic field. It took James Clerk Maxwell's theory to explain the nature of light and to project the image of the electromagnetic spectrum as a whole.
So we got the wavefronts, spherical wavefronts, and when you draw these lines, which are perpendicular to the wavefronts, these are known as the light rays. So light rays will be perpendicular to the wavefronts. So these are just arrows, and the distance between the wavefronts or distances are known as the wavelengths. So here's a wavelength between two wavefronts. All right, so you got the pulsating sphere generating the electromagnetic waves. Wavefronts of the electromagnetic waves are represented as squares over here, and the rays will be perpendicular to them. And these are also known as the plane wavefronts. Reflection, otherwise known as the law of reflection, the incident ray is going to be, it's coming in, it gets reflected from a mirror surface, and then it gets reflected out. So this is the incident ray, this is the reflected ray. Angles are measured with respect to the normal. So you got the angle of incidence and you have the angle of reflection, and they will be equal to each other according to the law of reflection. All right, so this is the one the one that we were discussing is known as specular, or the regular reflection, which means that the angle of incidence and reflection are the same. And you also have an irregular diffuse reflection, which means that not all the light after reflection is going back to the source itself. As a result, you don't get yourself a reflected image. Instead, you end up seeing a person or a wall or a car or whatnot.
About a century ago, Apollo astronauts set up reflectors on the moon. Today, they're targets for astronomers at the McDonnell Observatory, Texas. By bouncing laser beams off the reflectors, the speed at which the moon is receding can be measured to within a hair's breadth. The gap is widening by 1.5 inches a year.
Yeah, the moon is moving away for 1.5 inches a year.
From this, over 4.5 billion years, the moon in our skies has shrunk to this.
So speaking of the moon, there's one more question which is coming up.
They call it the black jet.
Right after this one.
They call it the black jet. The F-117 is the invisible man of the aviation world. The F-117 penetrated Iraqi air defenses undetected while making precision attacks.
As you see, the airplane is made almost entirely out of flat surfaces. Now, radar is an electromagnetic wave of energy, and when it hits a surface, it bounces off. When it hits a flat surface, it pretty much all bounces off in one direction.
While the F-117 is all angles, the B-2 stealth bomber is a smooth batwing, but both can slip through enemy air with relative impunity.
Stealth aircraft aren't really terribly fast or terribly maneuverable, but if they're invisible, it doesn't matter.
All right, so there are two questions here.
They call it
Number
F-117
one, this one is angled
penetrated
properly.
Iraqi air defenses undetected while making
And because the surfaces are angled,
precision attacks.
the angle of incidence becomes a factor.
As you see,
All right, because of the angle of incidence and because the surfaces are angled, incident ray and reflected ray are not going to be going in the same direction. So which means that radar is not going to go back to the radar source, or you're not going to be able to actually see the airplane or the fighter jet in this case directly. So it makes you somewhat become invisible to radar.
the airplane is made almost entirely out of flat surfaces. Now, radar
Angles.
But this one lacks that kind
The
of
B-2
sharp angle. So when we're dealing with this sort of
stealth
stuff,
bomber is a smooth batwing,
notice that it's extremely smooth.
but both can slip through enemy
So the question is, how does this become radar-based?
air with relative impunity.
So that's something that we will discuss about 3 lectures from now.
Even more important question. Since
So what is reflection on the atomic scale? This is something that we discussed before, so let's do
everything ever
everything on this one.
it might be charge oscillating, which creates a new outgoing wave. Notice the shadow that forms behind the oscillating charge.
All right, so the incoming electromagnetic wave is going to oscillate the charges inside a reflective surface, which is usually composed of, metal surfaces, which contains conduction electrons. So the conduction electrons will oscillate back and forth at the frequency of the incoming electromagnetic wave.
A line of electric charges. It might be electrons bound to atoms in a crystal.
All right, so notice that the oscillating charges will generate their own electromagnetic waves, radiating spherically.
Can produce outgoing plane wavefronts in new directions. And if the charges are free to move easily, as are electrons inside a metal, the result can be to stop the wave from penetrating at all. Instead, the wave is completely reflected.
As a result, the angle of incidence,
This is mirror reflection, in which the angle of incidence,
which happens to be this,
an even more important question.
will become equal to the angle of reflection. All right, so let's set up the mathematics for this one. So the first one is the law the laws of geometric optics. The law of reflection is what we're looking at. So here's the incident ray. This is the reflected ray. The angle of incidence is going to be the same as the angle of reflection. All right, so this becomes the law of reflection. So the question is why? What's happening between the light ray and the conduction electrons? So here's a metal surface containing all these conduction electrons, and the light is going to be coming in. We're only going to be interested in the electric field component of light, because the electric field is an electrostatic force field. Acting on the charges will cause the charges to actually oscillate in this direction. It's going to apply a force on the charge, it's going to accelerate, it's going to vibrate it, and the vibration or the acceleration of charges will emit electromagnetic waves again. So there's going to be an interaction between the outside electromagnetic wave and the newly generated electromagnetic wave. Waves interfere constructively and destructively. So the component of the waves, surviving component, is going to be in this direction. And as a result, the angle of incidence and the angle of reflection will be the same. So refraction is the next phenomenon. This is known as the bending of light rays from a straight line whenever the light changes medium. So the light is coming from air into water. So I represents the incident ray. This represents the refracted ray. So you got the angle of incidence. This is the angle of refraction. So we got a few observations. Light is going to bend towards the normal upon entering into a denser medium. So water is going to be a denser medium. Light is going to bend away from the normal upon entering into a less dense medium, which means that if you were to reverse direction, notice that the light is going to bend away from the normal. So the cause of this is the light slowing down in an optically denser medium. So how much the light slows down is denoted by this formula. So this is the speed of light in a vacuum. And V is the speed of light in an optically dense medium. So if you're looking at this ratio of speed of light in a vacuum to the speed of light in an optically dense medium, this is known as the index of refraction. So the index of refraction tells you how much the light slows down in an optically dense medium. Speaking of how much the light slows down in an optically denser medium, so you got two different media, M1 and M2. M2 is going to be denser than M1. So notice what happens, the light is going to end up changing direction, so it's going to end up bending towards the normal. All right, so how much the light bends towards the normal is denoted by this formula, which is known as the Snell's law. All right, so M1 is the refractive index of the first medium, and M2 is the refractive index of the second medium, index of refraction. Theta 1 is the angle of the incident ray. Theta 2 is going to be the angle of the refracted ray. All right, so speaking of speed, this is the speed of light in a vacuum. This is the speed of light in a denser medium. Speed can be expressed as a combination of wavelength times frequency. So in a vacuum, you got the wavelength of light and the frequency of light. In an optically denser medium, this is a discussion that we had before. If the frequency at the boundary is constant, the wavelength is going to get shorter. All right. So and how much shorter it's going to get is going to be related or dependent upon the index of refraction. All right. So which means that we can come up with an expression for the index of refraction. And notice that the frequency is going to be constant at the boundary for the reasons that we discussed earlier. As a result, we end up coming up with an expression regarding the new wavelength. And then we notice that the wavelength is going to shrink by the index of refraction. So it's going to become shorter. The wavelength is going to get shorter in an optically denser medium by the index of refraction. So bending of light rays from a straight line is what we refer to as refraction.
It's okay if you make a mess.
All right, so you
Put a penny in a pie pan. Now move back so you don't see the penny. Don't move, because I'm going to pour the water in. It's okay if you make a mess. Pretty cool, eh? See, light's always bouncing off the penny. But when you pour the water in, it makes the light bend. And the bending of the light makes the penny reappear. But the penny didn't move through all of this. But don't take my word for it. Try it.
All right, so the penny is located here, and you will get to see the penny over here. So what's going on there? All right, so the penny obviously is the source of light coming from a denser medium into a less dense medium. So light ray is traveling from more dense to less dense. So it's going to bend away from the normal into your eye. And your eye has a tendency to see things in a straight line. So the penny will appear to occupy a different position in water. So this is known as illusion. All right, so this is known as refraction. Deviation of a light ray from a straight line into your eye is the refraction. And what the eye does, or what the brain does with that information, becomes the illusion of reality that we've been discussing.